Hello and welcome to a new video on IGCSE Physics Classified Paper 4. In this video, we shall be discussing resistance of a wire. Another lamp X has a filament with twice the resistance of each lamp in the circuit of figure 7.1. The material and the temperature of the filament in lamp X is the same as the filaments in the lamps in figure 7.1. In Table 7.1, tick any box in the right-hand column that shows a possible difference between the filament of lamp X and a filament of one of the lamps in the circuit. So this is part of a question. We are not really interested in the rest of the question for the purpose of this video. We are just interested in this keyword here that we have twice the resistance. And we want to know what this translates into in terms of length and area. So you should know that the resistance of a wire or a lamp or anything is equal to a constant that you are not really required to understand very deeply. It's called resistivity, but it's not really part of your curriculum. You just need to know that it's a constant number. This constant here is multiplied by L and divided by A, and these are the two variables that we are interested in. So L is the length of the wire, and A is the area of the wire. So if we have three wires like this, these two wires here are of the same length, but this wire has more or greater area. So the resistance of this wire is going to decrease because the area is bigger. So the resistance of the second wire is smaller than the resistance of the first wire. In the second example, we have the same wire again, but we have another wire of the same area, but of a much greater length. So just assume that it's the same area here. A equals A, but the length is much bigger. So if the length is bigger, then the resistance is bigger. How do we know this? We know this from the formula because the length here is proportional to the resistance. So as the length increases, the resistance increases. However, the area and the resistance are inversely proportional to each other. So as the area increases, the resistance decreases. So here we have twice the resistance. So we must have either twice the length or half the area, because L and R are directly proportional, but A and R are inversely proportional. So it's either twice the length or half of the area. These would be the correct answers here. The resistance of a 1 meter length of resistance wire is 7.6 ohms. A length of the wire is taped to a meter rule. A crocodile clip is connected to one end of the resistance wire exactly at the 0 meter mark of the rule. Figure 7.1 shows the crocodile clip connected to terminal P. A second terminal Q is connected to a movable contact using a long length of connecting wire. The movable contact is in contact with the resistance wire at a length L from the 0 meter mark on the rule. The movable contact is placed at different points on the resistance wire. The resistance R of the length L of the wire depends on L. Sketch a graph to show how R varies with L for values of L between 0 and 1. Mark appropriate values on the axes of the graph. So like we said before, R equals rho times L over A. And from this rule here, we know that R and L are directly proportional. In this problem, the area does not change and the rho is a constant. We always said that the resistivity is always a constant number. So this is a constant value. And this is a constant value as well. These do not change. So we just have a relationship between R and L in this question, where as R increases, L increases, or the other way around, as L increases, R increases. So we have a straight line that looks something like this. It starts at 0, 0, and it ends at, when the length is 1, it ends at this point here, And we said, or we were told that the resistance, the total resistance is 7.6. So we are supposed to mark 7.6 on the graph like this. This would be the correct version of the graph between 0, 0 and 1 and 7.6. Wire P has a diameter D and a length L. A second piece of wire Q is made of the same material. So same material means that it has the same constant of resistivity. So it has the same value of rho. Rho is the same because they're made of the same material. And like we said, this variable rho, we will not be tested on it at all. So we'll always assume that it does not change because they have the same material. And we are told that the diameter of Q is half of the diameter of D, and the length is 5 times L. We want to calculate the resistance of wire Q, given that the resistance of wire P is equal to 330 ohms. So let's write down the rule. R of P, so RP equals rho P LP over AP, and RQ equals rho Q LQ over AQ. Now, the rho is the same in both, so it's the same material. Here, this is L, and this is A. Let's just write A for now. Here we have 5L, and we want to get a value here in terms of A. So A is equal to pi r squared because this is a wire and the cross section is a circle. So we have here the radius of the circle is r. And in the second wire, we know that it is equal to half the diameter. So the diameter is actually double the radius. So half the diameter just means half the radius. So since the wire has half the diameter of the other wire, it has half the radius as well. If we plug this into the formula here, we get pi times 0.5 r all squared, which is 0.25 pi r squared, which tells us that it's a quarter times pi r squared, or basically a quarter times the area of the original wire. So the main concept here is just to understand that since the diameter is multiplied by half, therefore the radius is multiplied by half as well. Therefore the area is multiplied by half all squared. Half all squared is 1 over 4. So you should know that the area is 1 over 4 of the original area. So we're just going to write 1 over 4a here. And then we want to take the numbers out. So we have 5 over 1 over 4 times rho L over A. Rho L over A is the resistance of the original wire, which is equal to 330 ohms. So this is just 5 over 1 over 4 multiplied by 330. So if you divide 5 by 1 over 4, this is the same as 5 times 4. So this is just 20 times 330. And you can use your calculator to figure this out. And this gives you 6,600 ohms. This would be the final answer here. And this is how we did it. So we said that the length is 5 times the original length, and the area is half squared of the original area, which is 0.25, like we said, or 1 over 4 of the original area. So we put 5L and we put quarter of the A, or 0.25A, and then 5 divided 0.25 gave us 20, and then we multiplied that by the amount that we were given for the first resistance, and we got the answer as 6,600 ohms. This is the final answer here. A wire of length 2 meters and cross-sectional area 0.4 has a resistance of 0.14. Calculate the resistance of another wire of the same material of length 3 and cross-sectional area 0.9. So in this case, it's easier to just calculate the value of rho. So we are given that R equals rho L over A, and we are given that they have the same material. So since they have the same material, therefore they have the same value of rho. So for the first wire, we can rewrite the equation as rho equals R times A over L. How did we obtain this equation? We took the A to the other side, so it became R times A, and then we divided by the L. And now we have only rho on the right-hand side. So rho equals R times A over L. R is 0.14. Excuse me, 0.14. A is 0.4, which is the area, and L is 2. Now we have the value of rho. So 0.14 times 0.4 divided by 2 gives us 0.028. Now that we have the value of rho, and we know that the other resistor has the same value of rho, so we can rewrite the equation. Actually, we can just write the original equation here. So just R equals rho L over A. We have the same value of rho that we calculated, which is 0.028. And the value of L is 3. And the value of A is 0.9. And we want to get the resistance. So we multiply 0.028 times 3 divided by 0.9. This gives us 0.092 ohms. And this would be the final answer here. A cylindrical metal wire, W1 of length L and cross-sectional area A has a resistance of 16 ohms. A second cylindrical wire, W2, having length L over 2 and cross-sectional area 2A, is made from the same metal. Determine the resistance of W2. So again, since they're made of the same metal, therefore they have the same value of rho. So rho is the same in both cases. The L becomes L over 2, and the area becomes 2A. And we just take the numbers out. So we have L over 2, this is the same as half rho L divided by 2A. So we want to evaluate this. Half divided by 2 is 1 over 4. So the answer would be 1 over 4 times rho L over A. Rho L over A is the initial resistance, which is 16 ohm. This was given in the problem. And therefore, the final answer would be quarter times 16, which is 4 ohms. In double I, we want the effective resistance of the two resistors when they're connected in parallel. So this is 1 over R1 plus 1 over R2. So this is equal to 1 over 16 plus 1 over 4. And you just use your calculator to find this, to figure this out. And you get a final answer of 3.2 ohms. And this brings us to the end of our video. I hope this has been beneficial. Thank you for watching.